Welcome back to a new video about Butterworth Response LC ladder filter design. This is our example number 6. In this example, we will discuss the Bandstop filter design using this LC ladder configuration. We will do that in our calculation step by step and also verify these in SPICE simulations. So let's look at our objective. The objective is a design of a Butterworth response of a passive LC ladder filter configuration for a bandstop filter, and we will use 50 ohm double terminated shunt input circuit. That means using this generalized filter circuit again, we have the source resistor which is normalized 1 ohm and also the load is 1 ohm. That will be upscaled to 50 ohm. That is actually the meaning of this specification here. There are also other specifications given here. The maximum passband ripple must be 2 dBs. The minimum stop and attenuation must be 30 dB, and we have the lower passband frequency 100 kHz. Upper passband frequency must be 600 kHz. The lower stop band frequency must be 200 kHz, and the upper stop band frequency must be 300 kHz. So we will see if we really met this also in the simulation results. Let's look at our solutions. We start as we did in the bandpass filter design with the bandwidth and the center frequency. The bandwidth is again between the lower and upper passband frequencies given in omegas, so in radians per second. So we calculate that. That will be then given here using the values shown in our specification. That will be then 10 to the power 6 pi radians per second. Okay, now moving on. The next step is then the center frequency. As we have discussed earlier, center frequency is given by the geometric mean of the upper and the lower passband frequency. So you multiply them and take the square root. Again in omega, so you multiply actually this by 2 pi, this by 2 pi. So you then substitute that in this formula and you will get the 1.539 mega radians per second. Okay, now we have the necessary information for step 1. Going to step 2 is the normalized passband frequency, capital letter omega of P, and normalized stop band frequency of omega S. This is for the prototype low pass filter. Still we are now in the low pass filter calculations. So this is the formula. We have done this also in the previous example. So for the band pass filter, so it's really similar. So this is then again here 1. The other one is for the omega S, which is then given here, and that is S. So we use here for omega S the stop band frequency specifications, lower and upper, and here we use the passband frequency specifications. Now the step 3 is the filter order of the prototype low pass filter. So the prototype low pass filter, for that we need the epsilon P related to the A max, which is the passband ripple. We know it is 2, so we can substitute that. You get now 0.7648, I must say. For epsilon S, we use the A minimum, and you substitute now this 30, and you get now 31.61. Now together, we can now calculate the filter order for this low pass filter configuration. That's the epsilon S and epsilon P, and this omega S and omega P. Now, we substitute the values we have for 5 here, we have a 1 here, and all those values here. Now we get here now 2.3123. That means we need to go up to 3 because we need to have an integer order. So we need to make a third order low pass filter, and that will be then transformed to a bandstop filter later. Now the normalized cutoff frequency again for this prototype low pass filter, that is given by this formula. So we see here the omega C and omega P, and we calculate now the required cutoff frequency normalized. That is then again using this epsilon P. We have now 1.0935 radians per second. Now the bandwidth scaling factor is KFBS. So for the bandpass filter it was KFBP. So the difference here is we don't multiply the omega BW with this omega C, but we divide it by. So you have actually now this expression. Now when you now use this 10 to the power 6 pi radians per second from the bandwidth, and also this 1.0935 from the omega C normalized cutoff frequency, you get now your scaling factor for this bandstop filter, which is then 2.873 megaradians per second. Now let's collect the data here. And again, we have this Km, which is our magnitude scaling factor. That's 50 because we go from the unity, the normalized values, to 50 ohm because it was the required value here. Okay, this is the table again. It is in this format given only for low pass filter, but we will transform that to the band stop filter. So that will be done shortly. And this third order row here is again what we require, the x1, x2 and x3. So these are the coefficients we will use for our calculations. Now the low pass to band stop transformation. This is the low pass filter. The transformation goes like this. You change the capacitors and the inductor here to get this band stop filter in this fashion. So you make your capacitor a series combination of the new capacitor and a new inductor. So between node A and B we will get this. So that means this will be transformed in a capacitor and an inductor in series. And the inductor will be then a parallel combination of the inductor and the capacitor. That's actually shown here. This is actually the reverse of what we did in the band pass filter. But the band pass filter, we said it is the capacitor that changes to a capacitor and an inductor in parallel, and the inductor was changed in an inductor and a capacitor in series. Now we do the reverse. That means this whole circuit will change in this circuit. You see here, this is now a series combination. Also this one, because it's capacitor, and this inductor will be then in parallel combination. You see that. And the RS and RL here, which are the normalized values of 1 ohm and 1 ohm each, that will be then RS prime, because that will also scale up by this 50. That will be then 50 ohm and 50 ohm. That is then the actual value. So let's now calculate all these components. So we have now in total 6 components. So 3 capacitors, 3 inductors, and RS and RL prime. Okay. Let's collect them here, and also the circuit what we want for our band stop filter. This is now the band stop filter we need to design, and also the values we need to calculate. First, the S1, which is then the series capacitor here, first one. It's calculated by this one because we have our scaling factor, we have our Km, we have our center frequency, so everything is known. And we also know that C1 here, which is actually this X1, which is our coefficient here, which is 1. That means we just calculate that by inserting that in this formula. You get now 24.26 nanofarads. Now the LS1 is then given by this formula. Again, use the C1 and also Km and the KFBS. And you get now 17.40 microhenries. Now for the CP1 and LP1, you get this and this formula. So again, you see there are, in some cases use the omega center squared, and other you only use the others. So this is now, these are the values for the CP1 and LP1, in a similar form for the CS2 and LS2. That's actually exact same because it doesn't change. Only change is actually here the C3 and C3, because L2 was 2, you see that, and C3 is also 1 because you look at the coefficients here. This is C1, this is L2, this is C3. Now we have the 6 components we required for this band stop filter. Now the RS prime and RL prime, that are just scaled by this Km 50. So you go from 1 times 50 is 50, and also RL prime will be 50. So now we have now all 8 component values. Okay, let's collect them here. These are the values we wanted, and this is the designed circuit. This is the band stop filter in the simulator. This is the prototype low pass filter. You see the 1 to 1 I must say, 1 farad, 2 henries and 1 farad, and 1 ohm and 1 ohm for the source and the load. And these are the scaled values we just calculated. Now we will simulate this circuit and see if this is really meet these specifications. So let's now jump to the simulation results. This is the Bode plot first. This is now the gain. You see the band stop configuration. So you have here pass band gain, and you have a point where it goes rapidly down. Let's look at the circuit again. This is the circuit, and also look at the specifications one by one. The pass band gain is indeed minus 6.02 dB. Why I say indeed? Because at the lower frequencies and at very high frequencies, the gain is here 0.5, because you get the 50 over 50 plus 50, which is then 0.5, 20 log 0.5 is minus 6.02 dB. So you have always have this gain of 0.5. That's correct. The lower passband frequency is 100 kHz, which is as required because we want also have a ripple of 2 dB. Let's check that, because if you go to the 100 kHz, which is here, this label, you go to the gain of minus 8.02 dB, which is 2 dBs down, looking from this flat line. So that's as required. And the upper passband frequency, it's here. You can see that here, that is at 600 kilohertz. That is also minus 8.02 dB, or again 2 dBs down as required. So we actually have the left and right hand side exact same ripple, and the frequencies are also correct as required. Now, looking at the lower stop band frequency, this is this one. This is 200 kilohertz. The gain there is minus 45.63 dB. So you go down by 45.63 minus 6.02 dB, so 39.61 dB. So at least 30 is met. So it means that is also what we wanted. So minimum is required 30, but you get 39.61 dBs. For the upper stop band frequency, this is 300 kilohertz, you see actually the exact same result. So again, minimum 30 dB is achieved here. You also have here the lower cutoff frequency and upper cutoff frequency is extra information, so you can see what your half power bandwidth is. Okay, and you also see the center frequency here, which is at this spike point, which is 244.963, almost 245 kilohertz. So that means, according to specifications we have, and also the simulation result, we can say this circuit will do the job, and also according to specifications. Alright, this is our example number 6 about the Butterworth response LC ladder bandpass filter, bandstop filter I must say, design. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.